Hello all, I'm here to give a brief explanation about the cache organization in Pentium Microprocessor. Okay, now what is basically a cache? A cache is nothing but a high-speed random access memory that contains the frequently stored instructions and data in your microprocessor. Okay, now you people have to think, or you might be even wondering, how the access time is reduced by making use of the cache. That seems to be pretty cool with the cache organization. Now, let me introduce you to some of the basic concepts on how you're going to map your physical memory to your cache memory. Before that, just take a look at the random access memory on how it has been separated into fixed sized units called as blocks. What is random access memory? It is a physical memory in which you are going to do all operations and save your results generally. Okay. Now, when you look into the random access memory, you are dividing the entire physical memory into equally sized units called as blocks. Each block is made up of a group of address locations. When it comes to Pentium microprocessor, the total address locations available are 2 power 32, which is nothing but 4 GB address locations. And we are going to see how these address locations are mapped together and placed in a cache such that you will be able to access the cache very quickly. The thing is, when it takes some 70 nanoseconds to access your main memory, it is going to take only 10 or 20 nanoseconds to access your cache. Okay, the thing is achieved by combining the address locations in the form of units called as blocks. Okay, now I'll let you know that how these blocks are made up of. As we saw, the block 0 is consisting of the address locations ranging from 0x 00000 to 0x 0003. Okay, similarly, I have some bits to represent the blocks. They are called as the block identification bits. And finally, I have some bits to represent the words, corresponding words present in the address locations. This scenario is just for an example to make you understand how the block is uh, constructed and what are all the things that are used to identify the various things in the block. Okay. Now, as you can see, we have various blocks and each and every block consists of only fixed number of address locations to make things easy. Let's move on to the mapping methods of a cache. The first mapping is called as the direct mapping. Mapping is a technique in which you're going to place the blocks into your cache. Okay, as we saw, the main memory is divided into fixed size units called as blocks. Cache is also divided into fixed size units called as lines. Each and every line is constructed such that it could occupy or allow one single block to be placed completely onto it. Now just look at this. This is an example of direct mapping in your cache. Here, the thing is that you can place only block 0, block 256, block 512 and block 768 into the line 0, which means I can place only block 0 or block 256 or block 512 or block 768 at a time in this line 0 alone, which means these four blocks cannot occupy any of the other lines other than the line that has been dedicated for them. Okay, so this is called as direct mapping. Similarly, block 1, block 257, block 513 or block 769, any of these four blocks could be placed in line 1. Similarly, all other blocks will be mapped to corresponding lines. So, the process of allocating the blocks dedicatedly to some particular lines in the cache is called as direct mapping. As you can see, when the mapping is done in this fashion, it is going to be the simplest form wherein the access time is reduced such that when you identify a particular line and when you identify the particular block, you can represent that as a cache hit. That is, when the block that you are searching for or the address location that you are searching for is present in the corresponding line in the cache, we call that to be a cache hit. Generally speaking, when the required data is present in the cache, it is called as a cache hit, and when it is not present, it is called as a cache miss. Okay, but the drawback here is, suppose block 0 occupies the line 0 at the instant t1. At the same instant t1, I am searching for an address location that is present in the block 768. Okay, but while searching in the cache in the line 0, I am not able to find the block 768. So, because block 0 is already present there. So, this scenario represents a cache miss. The solution for this is to trash the block 0 and fetch the block 768 contents from main memory and place it in your line 0. This is the solution to replace the block 0 in line 0 with block 768, because your cache always contains the frequently used data and instructions. In this case, block 0 is not frequently used because at that time I am accessing block 768, which means it takes the prestige of being frequently used. So I am replacing block 0 in the line 0 with block 768. This means that there is a disadvantage that even if other lines are empty, I cannot place block 768 in any of the other lines because I have dedicatedly allocated the blocks to be placed in a particular line. So this is going to be the drawback in your direct mapping. However, when the cases are going to be very simple, this kind of mapping is generally used. So we have one more thing called as fully associative mapping. I'll let you know what is fully associative mapping. This is a very easy method wherein if we take the previous case, any of these blocks can be placed in any of the corresponding or any of the lines available. This is called as fully associative mapping. It means that you are not allocating or reserving any blocks to be placed in a particular line. Instead, any of the blocks can be placed in any of the corresponding or any of the lines. Okay, which means you have the freedom to replace the currently searched block in any of the lines rather than going for thrashing as in your direct mapping. However, the drawback is that the hardware complexity increases because when you want to find out a particular block in the cache, you have to go through each and every line. Okay, so that is going to be the complex process in your fully associative mapping. To overcome that, we have another term called as set associative mapping. Set associative mapping is a term in which it adheres to the laws of both direct mapping as well as fully associative mapping. Here, the lines are usually grouped into powers of 2 and are called as sets. For example, they have grouped two lines together to form a single set. And when I say that this is a midway between direct mapping and fully associative mapping, I can clearly say that when it is following direct mapping, in the sense that I can place only block 0, block 256, block 512 and block 768 in this particular set, not in any of the other sets even if they are empty. So this follows the direct mapping. However, in which case or in which sense it adapts to the fully associative mapping is that I can place these blocks in any of these sets, but I can place the block in any of these lines in that set. So which means this form of associative mapping, set associative mapping, is a combination of both direct mapping as well as fully associative mapping. In fully associative mapping, the freedom is given such that the block could be placed in any of the lines. Here, the block could be placed in any of the lines within that particular set. So it follows some portion of your fully associative mapping. when it comes to the statement that it follows direct mapping, the blocks can be placed only in particular sets. So here it follows direct mapping. So this proves to be an efficient one over the previous direct mapping as well as fully associative mapping, and hence the Pentium follows the two-way set associative mapping in its cache organization. As you can see, this is the cache organization of direct mapped, fully associative and set associative. Just look at the 32-bit physical address. It has been divided into 27 and 5 bits. When we take the direct mapping, we have a thing called as index bit, or the bit that is used to represent the block, sorry, the line. Okay, so we have 5 bits. Again, these 5 bits are used to represent the words in the corresponding block. As I've already told, in Pentium we are grouping 32 address locations into a single block, which means we need 2 power 5 combinations of zeros and ones to represent those 32 address locations. That is why we are having offset bits of 5 in number. And finally, the 20 upper physical bits are used to match the address with the tag. Here the tag is nothing but the block which is placed from the main memory into this cache. So in a particular line, any of the blocks can be present that have been dedicatedly allocated for this line. So to find out which block is present, we are making use of a field called as tag. So whenever a block is placed into a line in a cache, a field called as tag will be automatically created and it will be placed in the cache. So this is all about this direct map. So when you are searching for a data in a cache, it will be searched in the manner that first the line or the index bit will be searched to identify the line in the cache. Next, the 20 bits will identify whether the tag matches with that of the physical address. If these two criteria holds good, it means that you are having a cache hit, which means the data that you are required is present in that, because you need not check these 5 bits because all the 32 address locations will be anyhow placed in that particular block that you are looking for. So this is all about this direct mapped cache. When it comes to fully associative cache, there is no need to have a line index because all the blocks have the freedom to be placed anywhere in any of the lines in the cache. That's why they have grouped 20 upper bit physical address with that of the lines, so that you are allocating this alone for the tag field itself. Okay, so this is how you'll be making use of this. So just have a look that in these two caches, the total number of lines in the cache have been made 128. Just come to the set associative cache. Here they have followed two-way set associative cache, which means the entire lines will be divided into two equal parts, such that the two equal parts of that is the two lines form a particular set. So this 063 represents the total number of sets, which means 64 sets represents 128 lines, and I have similarly the 6 bits to represent the set in which the data is present, and these 21 bits represents the physical address or the tag, out of which a single bit will represent the line in the set in which the corresponding block that we are searching for is present. So this is all about the basic cache organizations. Since the set associative cache is better than these two, we are making use of a two-way set associative cache for the cache organization in Pentium Microprocessor. This is the structure of your 8 KB instruction and data cache. So the total size of the cache is 16 KB in Pentium microprocessor, with each instruction and data cache having its own memory size of 8 KB. So when it comes to data cache, it will be looking like this. Like this, in the sense we have way 0 and way 1. Way 0 represents the line, one of the lines in the set, and way 1 represents the other line that is present in that set. Okay. Now here we are having 128 sets, 0 to 127, which means the total number of lines are 256, and each and every line is having 32 bytes address, 32 bytes of data, which means the total capacity of a particular single cache, single data or instruction cache is 8 KB. So this is all about the cache organization of your Pentium microprocessor. Hope this would be useful for you. Thank you all.